Back in Calc 1, we talked about functions where you provide one number as input and one number comes out as output. And the derivative of this function at the x value a was f prime of a equals the limit h approaches 0 of f of a plus h minus f of a all over h. Just to recall where this really comes from, for the x coordinate, I mean, this is really what you're taking the limit of is a slope of a secant line. And in the denominator, it's really a plus h minus a, and that simplifies to just h. In the numerator, you take those x values of a plus h and the x value a, and you apply f to get the y values, and we subtract so that we have a change in y in the numerator. So you may recall in Calc 1 learning the derivative of f at a specific x value a first, and then you find that repeating this process over and over for different x values gets to be much. So we postpone plugging in an x value called a until later, and we create this derivative function. So given the function f, we create a new function f prime. It's really just the formula we saw above, just replace all the a's with x's. And this is, of course, also denoted dy over dx. So we have f prime, that's the Newton notation. We have dy over dx, which is the Leibniz notation. Now what we're going to do is take a function that has two inputs and one output, right? So x is an input variable, y is an input variable, and now the output variable is z. And we're going to do the same kind of thing. We have what's called the partial derivative of f with respect to x at the point x comma y equals a comma b. So that is f sub x. That's meant to replace what was f prime earlier. And then instead of just at an x value a, we've got to have an x value a and a y value b. And look, this part looks fairly similar. Limit h approaches 0 of f of a plus h comma b minus f of a comma b all over h. And that's at a specific point, right? So that's at a specific input, where, by input we mean an x value a and a y value b. But there's also then going to be a partial derivative function with respect to x. That is, replace all the a's and b's with x's and y's. But you'll notice there's this little sub x here. And then notation-wise, this can be dz over dx. So there's f sub x as a notation that's meant to be like f prime, and then there's dz over dx, which is meant to be notation like dy over dx. Now, you'll notice that the d shapes are a little kind of funnier, and we'll talk about that in just a moment. Okay, given a function of two variables, we just saw the partial derivative of f with respect to x. Here it is, using its two notations, and then what its definition is, this limit h approaches 0, and so on and so forth. And there was no room on the last slide, but there's also a partial derivative of f with respect to the variable y. So that's dz over dy. And in the other notations, f sub y, and limit h approaches 0, f of x comma y plus h minus f of x comma y all over h. The thing to note, though, as similar as these look, is that in dz over dx, the y coordinate remains constant. So you'll see these two y's highlighted in red to really try to indicate, look, we're evaluating this function at the x value x plus h and the y value y, and then the next time we evaluate the function, it's at the x value x and the y value y. So the y coordinate remains constant, and that's actually key to figuring out how to practically compute this partial derivative. To compute dz over dx, you just differentiate really in the kind of usual sense while regarding y as a constant. And similarly, notice that in the f sub y formula, there's in the definition, there's the two x's highlighted red. Notice we're evaluating the function once before the minus sign and then once after the minus sign, but the x coordinate remains x, right? It remains constant. So to compute dz over dy, you differentiate as usual while regarding x as a constant. Now to talk about that bit of notation. So you may be used to in the past, dy over dx, and the d's looked kind of normal. This Leibniz notation has this curly shaped d instead of a regular d. It's just meant to, more than anything, let us know that we need to be a little cautious, a little bit careful when computing a partial derivative instead of a regular derivative. But you'll see that the process is very, very similar. And then the Newton notation, instead of a prime, you have a little subscript because we need to indicate here as well what variable with respect to. So the little subscript, the little x or the little y that's highlighted yellow, that indicates which variable the partial derivative is with respect to. So let's look at an example. This is really not going to be so bad. So f of x comma y equals x squared plus 3 times x times y to the 10th plus y minus 1. And let's find the partial derivative with respect to x and then find the partial derivative with respect to y. Okay, so partial derivative with respect to x. So if the first term is x squared, there's not even a y there. So to differentiate x squared, just use the power rule. Nothing strange happened, just 2x, okay? The next term, let's be a little careful. There's x's and y's. But right now, if we're doing the partial derivative with respect to x, this does say f sub x, we need to treat y as a constant. So 3 is a constant, sure. But y, if y is a constant, then y to the 10th is also a constant. So what we're really doing is this 3 as well as the y to the 10th in the second term of f, we're just copying those down, and then we just need to differentiate x. And the derivative of x is just 1. And then the next term is just a plain old y, and if y is a constant, the derivative of a constant is 0. So that's what the 0 is doing. And then after the minus sign, there's a 1, and to differentiate that constant 1, we get a 0. So the two zeros are here really for the same reason. It's that y is a constant right now, and 1 is certainly a constant. Okay, finding f sub x required treating y like a constant. In fact, if when you're getting started, you just want to think of it this way. Just imagine that you replaced all the y's with the constant pi just for a moment, right? Then to differentiate x squared 3x pi to the 10th plus pi minus 1, in Calc 1, what would you get? You'd get 2x plus 3 pi to the 10th plus 0 minus, ooh, this should be a 0 here. Sorry about that typo, right? But that should be a 0 just like the 0 up there. So think of, if you need to differentiate with respect to x, think of just momentarily replacing all the y's with a constant that doesn't appear in the problem, so pi might be a good example. And then what would you do there? Right? So then let's look at the partial derivative of f with respect to y. Now we need to treat all the x's as constant. So x squared is constant, its derivative is 0. If x is constant, we should copy 3x and then differentiate y to the 10th to be 10y to the 9th. So I just simplified the 3 times 10 as a 30. Y will differentiate to 1, and then 1 will differentiate to 0. Okay, so again, finding f sub y, so very similar idea. Treat x like a constant. That is, if we just for a moment replace all the x's with the constant e, then we'd be trying to talk about the derivative of e squared plus 3e y to the 10th plus y minus 1. And how would you differentiate that in Calc 1? It would look like this, right? So 0 plus 30e y to the 9th plus 1 minus 0. And then you could just take that and replace all the e's back with x's. So just follow up some bonus questions. We could just, we've answered the questions that were asked in the question, but we could just, now that we have f sub x and f sub y, these are new functions of two variables each, we can now evaluate these functions. We'll find f sub x of 4 comma negative 5. And this process isn't bad, right? It's just plug in. Here 2 times 4 plus 3 times negative 5 quantity to the 10th plus 0 minus, ooh, this should be a 0. There's a typo here with that one again. F sub y, take this, 0 plus 30 xy to the 9th plus 1 minus 0. Just replace every x with a 4, every y with a negative 5. Okay, let's look at a new function and do the same process. F of x comma y equals y times sine of x times y. We'll find the partial derivative with respect to x and the partial derivative with respect to y. And we'll do this specifically at this input pi comma 1/3. So first we need to find the partial derivative function. So let's find the partial derivative with respect to x. So notice, okay, we have to treat y like a constant, meaning, what would we have done had there been a constant like 10 here? We would have copied down the 10, right? So in the same way, we copy down this y. And then, sine of x y, we're going to need to apply the chain rule. So this would be cosine of xy times, and then we need to differentiate x times y. Remember, again, we're treating y like a constant. So the derivative of x times 7 would just be 7. So for the same reason, the derivative of x times y is just y, and we copy that y there. Now that we have the partial derivative function with respect to x, we can now evaluate this at pi comma 1/3. And yeah, all of the x's should get replaced with pi's, all the y's should get replaced with 1/3. And I skipped some computation here, but if everything looks right, you should get the number 1/18 for the end of this. The partial derivative with respect to y is a little more work. So the thing is, we had just computed the partial derivative with respect to x, and notice that x was just in one spot. And in front of the sign was a y, and that was treated like a constant. Now if we do the partial derivative with respect to y, then y is the variable, and x should be treated like a constant, meaning look at the format of, I mean, what would you do had this said y times sine of 7y? I mean, just making up a number for a moment for x. You'd have to use the product rule. So we should do that here, right? So the first times the derivative of second, y times cosine of xy times x, so this x pops out from the chain rule, plus, and then the second half of the product rule, right? So copy the second part, so sine of xy, there it is, times the derivative of the first, and y differentiates to 1. Okay, then we will evaluate this at pi comma 1/3. Looks something like this, and I left out maybe some details for you to think about, but I think you'll get pi over 6 plus root 3 over 2. Okay, so the summary of the first computation, in the other notation, instead of df over dx, we could write this as f sub x of pi comma 1/3, and that's going to be 1/18th, just skipping all the work in the middle. Okay, interactive question. If z equals f of x comma y, and let's say this represents the height of terrain at latitude, longitude, xy, I want you to interpret what f sub x of pi comma 1/3 equals 1/18th means. What should this mean? In other words, think about creating an answer that's really just interpreting what's going on. I don't want to see the computation. It's already up here. I want you to just take this 1/18th and put some meaning behind it, especially given we're saying that the function represents height. So your answer should mention pi, it should mention 1/3, it should mention 1/18th, and it should mention the word height or some word that's like height somewhere in it. Okay, so let's talk about an interpretation of dz over dx given z equals f of x comma y. So suppose that f of x comma y represents the average value of a person's estate, that is the net worth of a person at the time they pass, among people who make an annual income of x dollars, where y is that person's credit score. So then f of 50,000, 623 represents the value of a typical person's estate among people whose annual salary is 50,000 and credit score is 623. Then dz over dx at that same point, also denoted df over dx at that point, this would represent how much more, I mean instantaneously speaking, someone's estate value would be. What would be the increase in their estate value? How much would it change by if their salary increased from $50,000, I guess, to $50,001? Now, instead, suppose z equals f of x comma y represents the value of a veteran's estate, where y represents annual income, and x represents, say, a probability, which should be a number between 0 and 1, yeah, of access to a VA home loan. Then you should think about things like, what would the partial derivative of f with respect to x at the point 0.78 comma 50,000 mean? So I've switched kind of what x and y are, but think about what things like this would really mean and try to have an interpretation of these things, just like the interactive question.